Okay, let's take a look at question 15 in sample exam 3. So this question is a Hess's law question, a thermochemistry question, and then there's two parts to it. First, you have to find out the enthalpy of a target reaction, just like a standard Hess's law question would ask. And then afterwards, you have to use that enthalpy to then help you figure out enthalpy that would be generated by a specific quantity of reactants. Okay, so let's start with part A first, which is just asking about what would the enthalpy be for this particular reaction if you have these given reactions right here. Now, this is a fairly complex Hess's law problem because there's 5 different reactions given to you, so you have to think through how to manipulate or modify each reaction so that when you add them, you get your target reaction. The way we do this every time is we look at our actual target reaction. We'll try to see if there's certain things in the given reactions that would help us get to the target reaction. And let's take a look here. The first thing is I notice that I have calcium hydroxide in the reactant side with coefficient of 1. So I'm going to go to my given reaction and try to find a reaction that has just calcium hydroxide in it. And I notice that this reaction 3 has calcium hydroxide and none of the other reactions has that. So that helps me. That means that the only thing I need to do is to modify that reaction to make it look like my target. And to do that, I'm going to have to flip it, right? I'm going to reverse it. So the calcium hydroxide is in the reactant side. So let's do that. I'm going to reverse reaction 3. And when I do that, this is what it looks like. CaOH2 becomes CaO and H2O. And when I reverse something, remember my enthalpy change will become the negative of that value. So the original enthalpy is negative 653. Now it becomes positive 653.1 kilojoules. And then let's take a look at another species, which is C2H2 in my target reaction. So then I'm going to need to look up the reactions and see if there's one that has C2H2 in it. And matter of fact, there is one. That's reaction 4. And the C2H2 here is already in the reactant and it already has a coefficient of 1. So I don't need to do anything with that one. In other words, I'm just going to keep reaction 4. So C2H2, 5 halves O2 goes to 2CO2 plus H2O. And the delta H is the same, negative 1300 kilojoules. The next species in my target reaction is CaC2, and that one shows up only in reaction 1. So that's what I'm going to do. And it's already in the product, so I'm going to just keep reaction 1 as is. So Ca plus 2 carbon goes to CaC2. Delta H would remain the same, negative 62.8 kilojoules. So we see that our last species is H2O. So H2O is already part of the other two reactions that we use. So we're not going to be able to do anything with the H2O at this point. Now, the next clues you should look for, though, is you need to get rid of certain things, right? So if you look at your actual reactions at the end, for example, you don't have CaO here, right? So CaO is one of the species that you've written down here. But at the end, in the target reaction, there is no calcium oxide. So that means that calcium oxide has to be canceled. In order to cancel calcium oxide, I'm going to have to find a reaction that has calcium oxide in it that I haven't used yet. And so that would be reaction 2 right here. That has calcium oxide, except that the calcium oxide is in the product site. And to cancel my calcium oxide in here, I'm going to have to make that calcium oxide in reaction 2 in the reactant side. So that's what I'm going to do. I'm going to reverse reaction 2. So if I do that, I'm going to have calcium oxide goes to calcium plus half O2. My delta H would be the negative of the value in reaction 2, which means that it will be positive 635.5 kilojoule. And you see that what that allows me to do is then have CaO on this side, CaO on the opposite side for the first one. That would cancel out later on, which would be what we're looking for in this case, since we don't have CaO in our target equation. Another species that we need to cancel out is carbon. Of course, we only have one reaction left, and that's reaction 5. In reaction 5, we have carbon on the reactant side, but we need to cancel the carbon that we have in the reactant side, so we need to flip reaction 5. In addition, we also need to make sure that we have 2 carbons, so that means reaction 5 has to be multiplied by 2 across. So I'm going to reverse reaction 5. 5 and multiply by 2. And when I do that, this is what I have. 2CO2 becomes 2C and 2O2. And the delta H here is going to be the negative of the original delta H, which is positive 393.5. But then I also multiply that by 2. So the final value of that would be 787 kilojoules, and it's a positive number. And so let's see what happens here if we were to add up all of these, because we've done what we could in terms of using all the reactions and canceling out things we don't want and having things we want in the right positions. The other thing that could be canceled out here is the carbon dioxide. So you notice that you have carbon dioxide here and here, so those go away. Oxygen is another one. You have oxygen here, a half, another oxygen here, 2. Those are both on the product side. And then I have a 5/2 oxygen on the reactant side. 5/2 is the same as 2.5, so that would exactly cancel out with all of these guys. So then this is what's left. You circle this in different color. We got this guy left, this guy left. So actually one more thing I could cancel here. Calcium, one is in reactant, the other one is product. Okay, let me go back to find things that still exist. Water, both on the product side, and then CaC2. So let's write out all the species that exist at the end. CaOH2, calcium hydroxide, C2H2. Those are all the reactant species. 2H2O, and then CaC2. And what you see is that that's exactly this target reaction right here. So we got what we want. Now we just have to add up all the values that we have here for delta H. And so if you add up all of those numbers, you're going to get positive 712.8 kilojoules. Okay? All right, this is question B. It says, what's the delta H if you have a reaction between calcium hydroxide and C2H2, which is the reaction that we just figure out the delta H for, if the conditions are given as such, okay, in the question. So this is basically a stoichiometry question, but it's associated with energy calculation. So this is the concept of thermochemical equivalence, which just means that your reaction quantities, your stoichiometry, can be used to calculate the amount of energy needed for a reaction. So the one concept I want to remind you is that this value of delta H that we just found, 712.8 kilojoules, refers to per mole of reaction, which in the reaction means 1 mole of the calcium hydroxide and 1 mole of the C2H2 reactant. Okay, so that's how much energy you're going to need if you have 1 moles of each of those guys. Now the question is, how many moles do you actually have in the condition that's given in question B? So to do that, we're going to have to figure out our limiting reactant, right? Just like we would figure out calculations with stoichiometry. So let's do a limiting reactant calculation. So for CaOH2, I need to find its number moles. And the number moles is just going to be 1 molar times 0.025 liter. And that's just 0.025 moles. That's for CaOH2. And for C2H2, the number moles is, because it's a gas, it's given in this case as volume, 11.2 liter, but they tell you that it's STP, and if you remember at STP, all gases have a volume of 22.4 liter if there's 1 mole of them. And so that leaves you with half a mole of that gas. And then remember, in figuring out limiting reactant, what we do is we start with the number of moles, and then we have to divide that by the number of moles needed per reaction. So 1 mole is needed for calcium hydroxide because the coefficient is 1. So 1 mole per reaction. So we end up getting 0.025 reaction. And then for this one, C2H2, same thing. We have 1 mole needed per reaction. Again, the 1 comes from the coefficient of C2H2 in the reaction. So 0.5 reaction is what we're going to be able to have if we use up all the C2H2. So that means that the smaller one is going to be our limiting reactant. So the smaller one is calcium hydroxide in this case. So that's our limiting reactant. Okay. Once we figure out the limiting reactant, we can use that to find our actual energy. So the enthalpy that you would get is you start with the enthalpy that you calculated, which is 712.8 kilojoules per mole of reaction. And then we have to convert that to the per mole of the calcium hydroxide. So in the reaction, I have 1 mole of calcium hydroxide. And again, what that means is just that in the balance equation, the coefficient is 1. So that's why this is a 1-to-1 relationship. Now, the actual number of moles of calcium hydroxide that I use in the reaction is 0.025 mole, right? That's what we calculated earlier. So that's going to tell me me exactly how much energy is going to be produced. And you can see that by dimensional analysis, these units cancel out. And so at the end, I can figure out that I'm only going to need 7.82 kilojoules of energy, or enthalpy in this case, if the quantities of calcium hydroxide is 0.025 moles. Okay, so that's the answer to both of those questions.